I teach a course called, a relatively new course called Tools of Inquiry, in which I'm supposed to teach my students how to ask and explore their own mathematical questions. And historically, it replaced a course on Mathematica, and also the department would like the students to learn how to use some technology to explore some mathematical questions. So I'm going to talk a little about the sort of changes in that course design that's led to me doing an active introduction to SAGE. That's our goal for today. So in year one, having no idea how to go about accomplishing this, I'm not really knowing Mathematica, but the Mathematica skills at the beginning, I had some notebooks that were given to me, handed down unto me. We did some group inquiry exploration where we did small explorations together in class. And that supported the students doing individual inquiry projects that they sort of decided on the topic and they executed for themselves. And that was mostly outside of class, so in class, towards the end, they did some, what I call technology inquiry projects, where they built a Mathematica notebook that was supposed to guide somebody who was learning a basic topic to explore something and realize some of the big results. Many of the students are pre-service teachers, so they built things they can imagine their future students using. And of course, the Mathematica skills did support that, so there were some connections there. There were some problems, so desired changes. They needed another round of inquiry if they were really going to learn how to ask and explore their own questions. So I wanted there to be 3 rounds, one sort of explorations and then 2 projects. And then I wanted there to be less pressure on the technology. Originally I had them turn some things in with Mathematica, and they needed to be able to generate some relatively large things given what I said. We had a terrible problem with corruption, where about 30% of the time the Mathematica notebooks would corrupt when saved, and if they were being asked to turn that in, they were very unhappy with me. So I decided to move the Mathematica skills later and change sort of connectivity here. So in year 2, I had the group inquiry exploration at the beginning, which supported them doing group projects that they executed, which then supported them doing an individual project that they were more comfortable doing on their own because they'd executed one as a group. And then I just disconnected the Mathematica skills, but I put them at the end, and they did them in class and didn't have to turn anything in other than show me, I learned some stuff in Mathematica, look at what I accomplished with this notebook. So they didn't have to save, which fixed that problem. So some further desired changes. I really wanted them to use the technology for inquiry. It was disconnected, which I knew was a problem, but I didn't have a solution for it before I taught the course the second time. It became clear that they needed to think more about the programming language. I sort of assumed that math majors who had passed pre-calculus would really understand what a function is and understand, at least to some extent, the level of precision needed to make a computer do some mathematics. But even with the flashing red open bracket, they didn't know that meant maybe there was a pair that wasn't missing. There was like a lot to the intuition was just missing. They needed to think a little more carefully. And as a college and a department, we needed to reduce some costs, and we leaned towards open source, so we decided to move from Mathematica to SAGE, hence the SAGE being the title. So I just really want to connect this component and replace it with SAGE. So that's the structure we've got here. So again, the group inquiry supports the project, which supports the other project. The inquiry work supports, and that is going to now support the SAGE exploration. And if I'm lucky, they're learning SAGE while they're working on the individual, and they'll reach for some tools to support that work. So that's kind of the goal. So the rest of the talk is about that SAGE component, that SAGE block. So what are some required quantities for what we were going to be doing at that time? I thought I needed to find easy-to-state problems that were interesting beforehand, sort of inherently interesting to ask, as opposed to interesting because of the answer, or you had to know about the tools beforehand. And then, for it to be the technology component, the problem itself needed to call out for the technology. It needed to be obvious from the student's perspective, I cannot accomplish the exploration of this interesting problem without reaching for the technology. So I had 2 ideas, one about Fibonacci divisibility and one about random walks, both inspired by other things people said to me during the term, including a job candidate who came and talked about random walks, who we did hire. Fibonacci divisibility pattern. So earlier in the term, student had built this Excel spreadsheet. You can see Fibonacci numbers on the left. You can see the first 9 digits, and you can see some divisibility. So there's some patterns, right? The vertical spacing of these ones is regular, but there's some errors. For example, The number 8 is divisible by 8, but not 4 and 2. And so a little bit awkward and very time-consuming to do this by hand. Basically put each number in and use Wolfram Alpha to do the factoring as soon as they get large. So I reached out for the technology. He had originally been using Excel, and many of them were a little bit comfortable with Excel. So if you look down here towards the bottom, do you notice anything weird about these Fibonacci numbers? They have a lot of zeros in the end, and that's because Excel will only keep 15 digits of precision, and rounding is bad for divisibility. So, yes, and that convinced them they needed a more powerful tool. So we moved to Python/Sage. So on the left is 2 different versions of a definition of a function that produce Fibonacci numbers. One of them is very computationally intensive, and the other one is pretty straightforward. They learn about lists and if and while and interesting things in just setting that up. And then this is a piece of code that students wrote. It picks a random pair, or an integer, a relatively small integer, and a multiple of it, and picks a pair of Fibonacci numbers and computes whether or not they have the divisibility property as expected, and it adds 1 if they don't. And so they learn how to iterate that sort of large counting thing. And it turns out, if you're not familiar, I believe the result is that GCD of 2 Fibonacci numbers is a Fibonacci number associated with their GCD, which is a really cool result that's very difficult to state in this form for students to make sense of. But they could come to this through the technology. So that's, well, and then you might ask, well, how did they learn about Python? We use Sage Cloud, which is free, it was mentioned in the last talk, free access. And so the Khan Academy has 2 different videos that produce those 2 Fibonacci functions. And the students had notebooks open so they could basically code as it was going, but they knew that they were trying to answer this question of, like, what is the 377th Fibonacci number, and is it divisible by this other one? So while they were watching these videos, they were actually trying to answer the question that was already interesting to them, as opposed to just type this thing next. And so that's sort of what we did with Fibonacci numbers and Fibonacci divisibility. The other big idea that I had was having to do with random walks. So this code on the right generates a 2-dimensional random walk, or Drufford's walk, if you will. And then it graphs it, it removes the first, like a starting position, and then it counts how many times the starting position returns. So you can get a picture, and then it graphs it. So you can get a picture of the random walk, and then a little 0 next to it tells you that this walk did not, in fact, return to the origin. And so there's lots of interesting questions here that the students were able to generate. They said, how far do you walk? I.e., what's the sort of farthest away from your origin that you ever were? How often did you return? And does dimension matter? Right? And then you can see how they'd have to look at the code a little bit and then modify it, but it's pretty easy to see how they would modify those things. And then they'd have to employ that iteration technique as well to sort of one random walk, compute something of it, do another random walk, and sort of compute an average. So they did those things, and then they also sort of spontaneously did some statistics on the outcomes using Excel. So this top one is how many times I decided to leave the sort of relatively awkward student graph so you can see sort of what that actually looked like when they did it. This is counting the number of, given the length on the horizontal axis, the length of their walk, and the huge number of iterations of walks of the same length. On average, how many times did they return to the origin? And it appears to be sort of asymptotically approaching 2, or maybe a little bit lower than that, which is an interesting thing. And it does, in fact, depend on dimension, which is kind of a cool realization. It's interesting to see how it depends. And then these 2 are from different dimensions of 3D, or random walks, 3D and 2D. How was the furthest point away from the origin in the walk on average for that length? And they have a similar shape. And actually, if you zoom in on this one, it's sort of the R squared fit, and it's a really good R squared. And it's a little complicated, but that Y is essentially, the distance is approximately the square root of the length of the walk, which is not a result that was known to me before we started this project. But it makes sense given the distance formula. Essentially, you're imagining sort of randomly walking in a sphere, and there's a square root in any dimension, it doesn't matter which one. And that one turns out it does not depend on the dimension, which is really cool. 2 easy questions. And so, that's what we did with random walks. So I think we needed easy to state problems, because they were very low overhead at the beginning, interesting beforehand. They sort of wanted to know, yeah, what does happen in the trucker's walk or with this disability? And they called out for the technology. So in addition to the two ideas that I shared with you, many people suggested to me that I look at projectoiler.net, which has a lot of other low entry point but technology connected problems. And so that is eventually what I did to teach my students a little bit of Sage. And if you're, so thank you for listening. That's my email address if you have any questions. Elizabeth Thorin and I are running a contributed paper session and an issue of Primus called Teaching Inquiry. It's about teaching students to ask and explore their own questions. So if you're particularly interested in that aspect of this, we'd love to hear from you. Thank you very much.